Hi there, guys. Let's begin our chapter 2 lecture today. I'm going to begin with the warning on this chapter. This chapter has a lot of information, a lot of science in this chapter. Matter and energy are going to go over some chemistry with some biology mixed in there. Geology includes the earth sciences, which are a lot of science there. So we're going to be basically smashing everything into one chapter. Would I say this chapter is difficult? No, but would I say this chapter has a lot of information? Yeah. So generally, volume of information is where you guys might find a chapter more difficult. So let's begin with chapter two's lecture. We'll begin by defining matter. Matter is anything that takes space and has weight. Air, for example, we have air pressure, has weight, takes space. Air is considered matter. The law of conservation of matter you guys learned back in chemistry when you guys were balancing equations. It pretty much means if you have, for example, 4 irons on the left side here, well, you have to have 4 irons on the right side. You can't take matter and break it into other things, basically. It's not created nor destroyed. Oxygen is another example, 2 times 3, 6 oxygens. Over here, we have 3 times 2, we have 6 oxygens. So basically, matter is conserved when you write a balanced equation. Elements, you guys probably remember the periodic table of elements. Some of these elements, we have a lot of them on Earth. For example, oxygen is the most abundant element on the planet. We have a lot of hydrogen, we have a lot of silicon that's in our soil and in our rocks. Nitrogen is in the air. Hydrogen and oxygen, of course, are in water. Carbon is a lot of living matter, and oil and a lot of our carbon reserves inside of the Earth. So elements basically have their own properties, and they're not broken down into substances with other properties. An atom. Here's a picture of an atom. Okay, an atom here has 3 major particles. Protons are the positives, neutrons have no charge, and you have negative electrons floating around the nucleus. What's important here is the protons define the actual atom. So the number of protons tells you what you have. The number of neutrons, the number of electrons, well, that can vary at times, all right? So neutrons and electrons can vary, but protons will not vary, all right? So the atomic number, that's the number of protons, same thing. Neutrons, I'm going to tell you in a little bit how to calculate neutrons. And electrons, these negatively charged particles floating around the outside, well, the electrons are very light in weight. They don't have much to do with the mass of the atom. The mass of the atom is very dense inside of the nucleus. What is the job of electrons? Well, because they're on the outside, they determine how an atom will react. So when atoms react, these electrons are involved in the reaction. All right. When we talk about nuclear reactions, we'll talk about them later. We're going to be talking about what's happening here inside the nucleus. All right. Isotopes are elements, for example, that have different numbers of neutrons. So here's some examples down here. All right. And let's go through them. Sodium 23 versus sodium 25. All right. There's actually sodium 24 also, but we'll just talk about sodium 23 and 25. They're written this way. It's also written this way. All right. That number, the 23 or the 25, that is the mass number. The mass number is the protons plus the neutrons. All right. The atomic number, you'd find that on the periodic table. That's element number 11. If it's element number 11, it always has 11 protons and 11 electrons. Why do they have 11 electrons, 11 protons? Well, if you have 11 protons and they become neutralized, 11 protons are neutralized with 11 electrons. So therefore, the charges balance out. So these are atoms that are neutral. They don't have a charge. Now, how do you calculate the neutrons? Well, you take the mass, 23, minus the number of protons, 11, and that gives you 12 neutrons in this case. Sodium 25, 25 minus 11 gives you 14. Here's vanadium 51 and vanadium 53. Mass number 51, atomic number 23. It's the same for both vanadiums. The number of protons is the same because that's the atomic number. The number of electrons is the same because it always equates to the number of protons, but the neutrons are different. So that's what makes an isotope different. It's their differing numbers of neutrons, all right? 51 minus 23, 28. 53 minus 23, 30 number of neutrons. That's how you calculate these. Some elements are radioactive, which means they break down, they decay over time. When they decay, they eventually become something stable. During this decay process, they give off radiation. Some of this radiation can be very harmful to us depending on what is breaking down and the kind of reaction that's taking place. When does it become damaging? Well, when things that are radioactive or radioactive isotopes, when they enter our bodies through eating, through breathing, they can become potentially very dangerous. So when we have like a nuclear reactor accident, and we have a lot of nuclear waste floating around the air, and this is very, very, very dangerous. That particular nuclear waste will definitely kill you. All right. Half-life. All right. Half-life is how long it takes for something to break down in half. So when if you start with 100 atoms, how long does it take to get to 50 atoms? So basically, it's a time. There's going to be some math problems in this chapter. I'm going to go over a few of them here and show you how they're done. The work is in red for you. So let's talk about this. Cesium-137 is a radioisotope found in the ocean after nuclear accidents and weapons testing. It has a half-life of about 30 years. If the military has a nuclear accident and releases 1,000 kilograms of cesium-137 into the ocean, in how many years will there be 125 kilograms of cesium-137? Okay, so we start with 1,000 and we got to get to 125. All right, so the first half-life, 1,000 divided by 2 is 500. Now we have 500 kilograms after one half-life. 500 divided by 2 gives us 250. Now we're at 250 kilograms after two half-lives. 250 divided by 2 gives us 125. So to get to 125, we had 3 half-lives. Each half-life, according to the problem, is 30 years. 3 half-lives times 30 years gives us a 90-year answer. All right. Second one, carbon-14 has a half-life of 5,730 years. In how many years will a known sample contain 1/16 of the original carbon-14? Okay. Key, what you got to figure out is 1/16. How many half-lives is that? All right. Well, one half-life is 1/2 remains. Second half-life, you have now a quarter remaining. All right. Another half-life. For another half-life, whoops, we'll go back there. After another half-life, so we're at one half-life, half remaining. Second half-life, a quarter remaining. Third half-life, an eighth remaining. Fourth half-life, a 16th remaining. So we know that to get to 1/16, you had 4 half-lives. Each one is 5,730 years, so 4 times 5,730 is 28,650 years. You will have a bunch of these to practice, and you will have a bunch of these on your test. AP expects you to be able to use math logic in basically answering questions and figuring things out. So these are the first types of math problems we will have in our class. Okay, here's another half-life question. Finasteride is a medicine used to treat prostate cancer in men, and it has a 3-day half-life. All right. If someone initially ingests a 40 milligram tablet of finasteride, how much will remain in their body after 15 days? First thing you got to figure out is 15 days. How many half-lives is that? Well, if 3 days is one half-life, 15 divided by 3 gives us 5 half-lives. So at first there's 40 milligrams. After one half-life, there's 20. After a second half-life, 20 divided by 2 gives us 10. Third half-life, 10 divided by 2 gives us 5. Fourth half-life, 5 divided by 2 gives us 2.5. And the fifth half-life, 2.5 divided by 2 gives us 1.25 milligrams as our answer. So after 15 days and 5 half-lives, 1.25 milligrams of this medicine will remain in the person's blood. Now, let's move on. We are not doing math. That's the math for our chapter. Ions. You learned this in chemistry. Ions are anything that loses or gains an electron. And this is showing you sodium here loses its outermost electron. So if it minuses a -1, sodium becomes a +1 charge. Why does it do that? Well, it wants to have a happy outer electron shell, a full outer electron shell. So in order to have a full outer electron shell, it releases this one that's sitting here by itself in that outermost electron shell. So it releases this one, and therefore the next level is full, making sodium happy. So things that lose electrons become more positive. Things that gain electrons become more negative. Chlorine -1 is an example of something that has gained an electron. Calcium +2 has lost 2 electrons. That's why it's a +2. The amount of radiation it takes to remove electrons is called ionizing radiation, and this could be potentially dangerous. You don't necessarily want to be removing electrons and from things all the time. That could become dangerous. Radiation, for example, ultraviolet light can do that to the DNA of our cells and cause problems, cause cancer and things of that nature. So you don't want to be exposed to too much ionizing radiation. All right, now molecules versus compounds. Well, let's go over these terms. People have problems with these terms. All right, a molecule, two or more atoms chemically combined. For example, oxygen. Oxygen is a molecule, two or more oxygens combined. Water down here. Water is also a molecule because there's two or more atoms chemically combined. So they don't have to be the same thing to be a molecule. But if they're the same thing, it's okay. We will call it a molecule. The difference between a molecule, for example, water can have more than one element in it and still be a molecule. Compounds have to have two or more different elements. All right. So water is a compound. Water is also a molecule. Oxygen is a molecule. Oxygen is not a compound. It's not a compound because they are not different. Since these are the same, we will call it only a molecule. Water can be a molecule. Water can also be a compound. They're different, making it a compound. And there's also two or more, making it a molecule. Covalent bonds. These are bonds that occur when electrons are shared between atoms. Let's give you an example of them. Hydrogens and oxygens, they're covalently bonded together right here. All right, it's showing you to you right here. One of them has a stronger pull of the electrons. That is the oxygen. How do we know? Well, oxygen can pull more negative towards it, making the oxygen have a negative charge. Hydrogens, they've lost their negative, so they have more of a positive charge. So this is what gives water its polarity, its ability to have a positive and a negative side. The negative is always associated with the oxygen because it can pull more of the electrons towards it in that covalent bond. And hydrogen will lose its electrons, making it more positive on that side of the molecule. A hydrogen bond occurs between these positives and these negatives between water molecules. So the covalent bond is within the water molecule. The hydrogen bond is between two different water molecules. It basically exerts the positive and the negative attraction towards each other. Hydrogen bonds are very weak bonds. Covalent bonds are very strong bonds. That's a big difference there too. Ionic bonds, I would say these are the medium strength bond. They're stronger than hydrogen, not as strong as a covalent bond. This is when one element, like sodium, for example, will lose an electron. Chlorine will pick up an electron. Now they can bond to each other, making each other happy. What do I mean by happy? 2, 4, 6, 8 valence outer electrons happy here, sodium. 2, 4, 6, 8 electrons on the outside of chlorine, making chlorine happy. They want to have what's called 8 electrons in their outer valence shell to be happy. How does chlorine make itself happy? By taking one of these electrons that came here and adding it to the chlorine. So this forms sodium chloride. You put this in water, and what do you make? A solution. Solutions dissolve. Solution is a dissolved mixture, basically. Right? A dissolved mixture means you've added something ionic or something polar to water. When you add something basically ionic, like sodium chloride, or polar, like sugar, to water, it will dissolve. Water has positive and negative charges. They can stick to the positive and the negative charges in the sodium and the chloride and to the positive and negatives in sugar. All right? That gets us into water's properties. All right, properties of water. You learned these way back in, I believe, in biology when you took biology. Water, we just said it. It can dissolve a lot of things. What can it dissolve? Anything that is polar or ionic. All right, I just said that to you earlier. Water. This is why we live in San Diego. San Diego, it has perfect weather. One of the main reasons is we live next to an ocean, and our ocean doesn't usually get that cold. It doesn't usually get that hot. Since the ocean doesn't get very cold, it doesn't get very hot. That water, that large body of water off our coastline, helps basically, it becomes a heat buffer. So San Diego doesn't get too hot. San Diego doesn't get too cold. The ocean moderates our climate here in San Diego. Another factor with water. Water is one of the unique one of the unique compounds that when it becomes a solid, it actually becomes less dense. floating on its liquid form. Most things in nature, when they become a solid, they get more compact. They become tighter. Their molecules get tighter together. Therefore, they're denser, and they will sink in their liquid version. Water, because of the crystals, it actually, when it becomes a solid, the particles become farther apart, making it less dense, and that is why it will float on its liquid form. Water also, if you take water and you break it apart into its pieces or its ions, one ion is called a hydronium or hydrogen ion. Okay? So this is not only called hydrogen, it's called hydronium sometimes. Hydroxide ions are right here. Well, this is half. Two H's and an O makes water. So this is one ion of water. This is the other ion of water. When water ionizes, this creates pH. This creates acids and bases, basically. Anything with more H pluses or hydronium ions or hydrogen ions is considered an acid. If it has more hydroxide ions present, then it is considered a base. Acids have a pH value of less than 7. Bases have a pH value of greater than 7. If it's right at 7, it is neutral. So pure water has equal hydrogen or hydronium ions as it does hydroxide ions. They're equal. That's what makes pure water a pH 7 and neutral. Look at these examples here of things that are acids and bases. Seawater in the ocean is a pH of 8. Soap and cleaners, right up here, upper basic area, a lot of these cleaners that we use. Acid rain is down here. We'll talk about this later, a pH of around 4. Normal rain is about 5.5, 5.6 pH, but acid rain is when it gets down to the 4s. And now look at stomach acid and lemon juice and battery acid, very, very acidic. And just so you know, every time you drop one factor of pH from a 7 to a 6, something becomes 10 times more acidic. So it is a factor of 10. When you go up from 7 to an 8, it becomes 10 times more basic. All right, let's talk about from a 7 to a 5. 7 to a 6 is 10 times stronger. When you go from a 7 to a 5, it's 10 times 10. It's 100 times more acidic. When you go from a 7 to a 4, it's 10 times 10 times 10, 1,000 more times acidic. So each jump is a factor of 10. You need to multiply it out. All right. So once again, let's repeat that. From a 7 to a 6 is 10 times more acidic. From a 7 to a 5 is 10 times 10, making 100 times. From a 7 to a 4, 10 times 10 times 10, 1,000. 7 to a 3 is a 10 times 10 was 100 times 10 is 1,000 times 10 was 10,000 times more acidic. All right, and that's the end of our lecture right now.